Okay, today we're going to continue on with our knowledge about polynomials, and we're going to be looking at things called multiple roots. So the learning intention for today is to build our knowledge of multiplicity of roots of a polynomial. Okay, so we'll be successful if we can correctly factorize a polynomial to find its roots or its zeros. Another word for roots would be the zeros. Graphically, it's the x-intercepts. Correctly understand what multiple roots are. Correctly sketch a polynomial. That's how we will be successful. Okay, so some background knowledge. So if a polynomial p of x equals x minus k all squared multiplied by q of x, then p of x equals 0 has a double root because of this kind of quadratic part here at x equals k. So it means that we have two equal roots. And so what we have, for example, if we have this f of x, we've got 2x minus x minus 2 all squared and multiplied by a scalar of 3, we would have something that looks, so there'll still be a double root like normal quadratic. Positive 2. It just means that the rate of change will make it much more narrower in its dimensions apart from each other. In this way, we've got f of x equals negative 4, x plus 1. So we're going to have a double root at negative 1. Yeah. And once again, we'll have it touching it and then bouncing back off. So if we had, say for example, if we did something such as f of x equals x minus 2 all squared, so the x-intercept of 2, and we had x minus 5. Yeah. What would have is would have x-intercept of 2, x-intercept of 5. As it's a negative, I'll do it this way. It's going to bounce twice. It's going to touch the x-intercept and bounce back off it, and then cut through the next one. Okay, and that's your polynomial for there. All right. The other rule is if p of x equals x minus k to the power of 3 q of x, then p of x equals 0 has a triple root at x equals k, which has been 3 equal roots. So for example, we have this cubic of x minus 1, a scalar of negative 2. So x would be, intercept will be 1. It's a negative cubic, so it's going to go this way. So of a scale of 2. So it's going to come down and cross it. So the concavity will change, but it will still keep decreasing. And this one will have 3x plus 2, so we've got negative 2, and here it's a positive, so same thing, it will cut through. If it's a triple root, it will cut through and change concavity. So the rules are, if p of x equals x minus k to the power of r times q of x, then p of x equals 0 has a multiplicity root at x equals k, where the r is equal roots. So p of x has a root with multiplicity of r at x equals k. We'll do some examples. Example 1. If the polynomial of x to the power 4 plus 5x cubed plus 6x squared minus 4x minus 8, we want to sketch and state if it has any multiple roots. So to sketch a polynomial, we have to look at the constant and find the factors of the constant. So it's negative 8. So we've got 1, factors 1 and 2, 4. Yep. And so we're going to test it by subbing in, let's say x equals 1. So 1 to the power of 4 plus 5 lots of 1 cubed plus 6 lots of 1 squared minus 4 lots of 1 minus 8 gives me 0. So therefore p of 1 would be is a root. So we should be able to divide this by x minus 1. So x power 4 cubed, the squared, singular, and constant. Okay, so x goes into x4, x cubed times. Multiply that and subtract the top from the bottom. So minus minus becomes a positive, so it's 6x cubed. So it's 6x squared, 6x cubed minus 6x squared, minus those two from each other becomes positive, plus 12x squared minus 12x, subtract both, that's going to become positive, so it becomes 8x minus 8. Okay, so plus 8. Yeah, okay, that will give us 0. So now we have x minus 1 multiplied by that. So we can just test for this part of the polynomial. So let's see if x equals 1. 1 cubed plus 6 lots of 1 squared plus 12 lots of 1 plus 8 is 27, so that's not a factor. Let's try negative 1. That's 1, so that's not a factor. Let's try negative 2. So negative 2 is, so we can go x plus 2, sorry, x plus 2 in x cubed plus 6x squared plus 12x plus 8, x squared, x cubed plus 2x squared, subtract each, so 6 minus 2 is 4x, x goes into 4x squared 4x times, so 4x squared plus 8x, subtract, gives you 4x plus 4, yeah. Okay, so what we have is we have x minus 1, x plus 2, multiplied by x squared plus 4x plus 4. Now, x plus 2, so this is a perfect square of x plus 2 times x plus 2. So what technically it ends up becoming is x minus 1, x plus 2 to the power of 3, sorry, get rid of that, 3. So it's got a triple root at x equals negative 2. So if we just sketch it, we have -2. We have another root at 1. It is positive, so it's going to increase this angle. So what it looks like it happens is we get, we have a y-intercept of -8. So we have a polynomial that looks like that. And we have, triple roots, sorry. Sorry, we have, okay. So it's going to change concavity. Cross at 1, -8, and come back up at 1. Okay. Next example. We have a polynomial. It has a double root at x equals 2 and a double root at x equals -3. Its leading term is 4x to the power 5, so it should have 5 roots. So it should be, we need to sketch the graph by showing the polynomial has another root. Okay. So I'm going to do a large sketch. So if we have a double root at 2 and another double root at -3, so we can have something that looks like this. Or like that. Now, because it has a leading term that's positive, it means it must increase in the first quadrant. So we have this double root kind of happening. If that was the case, then we really want to have another, so it'll be decreasing here. So we'll have a double root here, and we obviously need to cut again to join these two parts together. Now we just don't know where that would be. Okay, so that shows, by sketching the graph, show that the polynomial has another root, and it would be somewhere here. Okay, thank you. That's it.